We learned in the last video that a spherical wrist is used so that we can control all parts of the position of a manipulator, the 3 linear positions and the 3 rotational positions. In Robotics 1, we learned how we could do inverse kinematics on a manipulator with as many as 3 joints by looking at it from the top view and from the side view, and then using trigonometry to find angles that relate the x, y, z positions of the end effector to the joint variables. You might be remembering this and thinking that if we tried to do that with a 6 degree of freedom manipulator, it would get really complicated, and you would be right. In fact, because 3 of our positioning variables are not linear positions along an axis, but are rotations around an axis, this method will fail altogether when we try to do it with more than 3 degrees of freedom. So instead, we have a modified procedure that we use to deal with more than 3 degrees of freedom. First, in order to be able to do inverse kinematics at all with more than 3 degrees of freedom, we have to start by making an important assumption. We assume that the first 3 joints are entirely responsible for positioning the end effector in space in the 3 linear directions. And whatever additional joints there are entirely responsible for rotating or orienting the end effector. In fact, this is one of the reasons that a spherical wrist is so common a device in manipulator designs you'll see in industry. In the last video, we learned that a spherical wrist is designed to try and make the link lengths as close to 0 as possible. And it's designed to allow 3 independent rotations. This is done so that it will be true that the spherical wrist has no effect on the positioning of the end effector in the 3 linear positioning directions. It only has an effect on the rotation of the end effector. So let's assume that we've designed a manipulator so that our assumption is valid. Here's how inverse kinematics works with 6 degrees of freedom. I'm first going to break down the procedure into 7 steps, and then I'm going to give you an example where we do it for a manipulator, and I think that will help make it more clear. Step 1 is that we draw a kinematic diagram of only the first 3 joints, and we do inverse kinematics for position, as we learned previously. Step 2 is to do forward kinematics on the first 3 joints to get only the rotation part. Step 3, find the inverse of this R03 matrix that we get from step 2. Step 4 is to do forward kinematics on the last 3 joints only and get its rotation part. Step 5 is to specify what you want the whole rotation matrix R06 to be. Step 6, given a desired XYZ position, solve for the first 3 joints using the inverse kinematics that you got in step 1. And then in step 7, plug those values in and use the rotation matrix to solve for the last 3 joints. Now, to help you understand how this works, I'm going to do an example, and then we're going to write some Python code to solve it. If you haven't taken Robotics 1 recently, and you're watching this on robogrok.com, there's a link next to this video to take you to where we learned how to get started and set up with Python, and you should do that before we start writing the code in this video. Now let's do the example of a cylindrical manipulator with a spherical wrist. So the kinematic diagram looks like this. The cylindrical manipulator part is right here, and the spherical wrist part is right here. Let's put frames on this according to the Denevitt-Hartenberg rules. Now, let's do step 1 of our inverse kinematics procedure. Draw the kinematic diagram of only the first 3 joints and do inverse kinematics for position. So here's the kinematic diagram of the first 3 joints. Now I need to point out something important here. Frame 3, which is on the end effector in this diagram, is exactly the same as the frame 3 in the previous diagram of the whole manipulator with the wrist. The only thing we've changed from the first diagram to this one is that I didn't draw the other joints, the spherical wrist. Now let's do the inverse kinematics for position for this diagram. I'll draw this from the top view first. I draw the top view so that I can see the variables θ2 and d3. Right away, I label the x and y position of the end effector since those are my most important known values. They're the input to inverse kinematics. This allows me to draw a triangle that is a right triangle and find the 2 equations. θ2 equals the inverse tangent of y over x, and d3 is equal to the square root of x squared plus y squared minus a3 minus a4. Now I draw the side view to get d1. In the side view, I'm only going to pay attention to the vertical position, z, because the rotation of θ2 means that I don't know whether this left and right direction is actually x or y or some combination of x, y. But using just z, I can get an equation for d1. d1 equals z minus a2 minus a1. All right, we're done with step 1. Let's move on to step 2. Do forward kinematics on the first 3 joints just to get the rotation part. We could use Denevit-Hartenberg here, or we could use the rotation matrix method that we learned in Robotics 1. Either way, we'll get the same answer. You should come up with R03 being this. Now the next step in our procedure is to find the inverse of R03. Let me show you why we do that. We know that R06 is equal to R03 times R36. We've just found R03. All the parts of this matrix are known since we can find θ2 using the inverse kinematics equation that we found a moment ago. And R06 is what we want the rotation of the end effector to be. So we'd like to solve this equation for R36. We've learned previously how we can rearrange matrix equations by using the inverse. Let's left multiply both sides of this equation by the inverse of R03. Then we would get this equation. R36 is equal to the inverse of R03 times R06. Could we figure out what the inverse of R03 is? We could do this by hand, but we're going to write it into our code in a bit. So for now, I'm going to leave the equation in this form. Okay, the next step is to find R36. I can do this by looking at our original kinematic diagram and only going from frame 3 to frame 6. You can do this by Denevit-Hartenberg or by using the rotation matrix method that we learned in Robotics 1. Either way, you should find R36 to be this. Now I know this is crazy and complicated, but don't worry about that too much yet. In a moment, we'll see how we're going to use R36. For now, let's move on to the next step, which is to specify what we want R06 to be. Let's suppose that we have a spray paint can on the end effector and that the paint is spraying in the Z6 direction. And suppose that we want to paint the ceiling. So we want the Z6 direction to be the same as the Z0 direction. We could then specify what we want the R06 matrix to be in order to accomplish this. For example, R06 might be this. That would put the Z6 axis in the same direction as the Z0 axis, while X6 is in the opposite direction as X0, and Y6 is in the opposite direction as Y0. We can make R06 be anything we want it to be as long as it's a valid rotation matrix. Remember that in Robotics 1, we spent some time talking about what a matrix needs to have in order to be a valid rotation matrix. Basically, it needs to have two qualities. The first is that every row and every column needs to have a vector length of 1. A vector length is found by squaring each element, adding the elements together and square rooting them. Secondly, in order to be a valid rotation matrix, the matrix needs to describe a right-hand coordinate frame. You can double check to see if a rotation matrix is a right-hand coordinate frame by using our shortcut method of writing rotation matrices in reverse. In other words, draw one frame that is a right-hand coordinate frame, and then figure out what the second frame would be using our shortcut method, and then check to see if the second frame does or does not follow the right-hand rule. Now, as long as you have a rotation matrix for R06 that really does qualify as a valid rotation matrix, we can move on to the next step. This is a good point to start writing some code to solve this problem. If you haven't gotten started up with Python yet, pause here and click on the link next to this video to watch the Getting Started with Python video first. Once you're all set up with Python and NumPy, come back here and we'll write some code to solve this problem. Okay, open idle and click on File, then New File, and you'll get a window that looks like mine. The first thing we need in our code is import NumPy as NP. Now we have an equation that says that R36 is equal to the inverse of R03 times R06. Let's do that in our code. We'll do R36 is equal to NP dot. That takes the dot product of two matrices. The first matrix will create a variable that's called INV R03, which will be the inverse of matrix R03, and we want to multiply that by R06. Now we haven't yet said what the inverse of R03 or R06 are, so let's go up above this line and specify those things. Let's do R06. In Python, our whole matrix needs to be enclosed in square brackets, and each row of the matrix also needs to be in its own square brackets. So our first row of R06 will be negative 1.0, comma 0.0, comma 0.0. That's the first row. This is supposed to be a negative here. Then I put a comma before I put the next row. And it's okay for me to put the next row on the next line, and that can make it easier to read. So I'll put another set of square brackets, and row 2 will be 0.0, comma, negative 1.0, comma, 0.0. Finally, the third row of R06 is 0, comma, 1, 0, comma, 0, comma, 1. Now, I want to say what the inverse of R03 is. But in order to do that, I first have to say what R03 is. Let's do R03 is equal to And here I'm just going to copy into my code what we already calculated R03 to be. It's the negative sign of theta 2. So I'll do negative NP dot sine theta 2, comma 0.0, comma NP dot cosine of theta 2. And that's the end of my first row. So I put a comma after the square bracket, hit enter, and go on to the next row. Row 2 is NP dot cosine theta 2, comma 0.0, comma NP dot sine of theta 2, that's the end of row 2. And then row 3 is 0.0, 1.0, 0.0. Now I can get the inverse of R03 like this. The inverse R03 is equal to NP dot linalg, L-I-N-A-L-G, dot INV R03. Now we use the variable theta 2, and we haven't yet said what theta 2 is. In our inverse kinematics procedure, we get theta 2 from our desired XY position. So let's go back up near the top and use the position inverse kinematics to solve for theta 2. We found out that theta 2 is equal to the arctangent. We'll do NP dot arctan 2 y over x, and you specify that in Python by doing y comma x. So we need to give a desired position of x and y. Let's say for now that x is equal to 5.0 and y is equal to 0.0. You could put any values you want in here for x and y for now, because we're just taking a look at how we can solve for the rotational part of inverse kinematics. Okay, this code is going to give us actual numbers for R36, and I want to see what those actual numbers are. So for my last line here, I'm going to say print R36 equals, and then I'll do comma np dot matrix R36. Now let's run this code. It will force you to save it, and then you'll be able to run it. So click on Run and then Run Module. Go ahead and save it. Your result should look like this. You have a bunch of numbers for the matrix R36. But remember that previously we found a matrix R36 that was full of variables, and the variables that were in this matrix were theta 4, theta 5, and theta 6. Those are the variables we're trying to solve for. We can find values for theta 4, theta 5, and theta 6 by making a one-to-one correspondence between the matrix that we found with variables in it and the matrix that we just found now with numbers in it. We'll start with the simplest expression in our variable matrix. The simplest expression is in the lower right-hand corner. It just says cosine theta 5. The number in our matrix in that same position is 0. This allows us to write an equation that says that the cosine of theta 5 must be 0. Let's write that equation into our code. So theta 5 is equal to the arc cosine of the value that is in the lower right-hand corner of the R36 matrix. We'll say theta 5 is equal to NP dot arc cosine of the matrix R36. The value that's in the third row, we put a 2 here because the first row is row 0 in Python. So 2 is actually the third row and the third column. Then, after we've calculated theta 5, I want to print it. So I'll print theta 5 equals, then we'll print the value theta 5, and then we'll put a note on here of what our units are, radians. Now run the code. Here's our R36 matrix, and it says that theta 5 has to be 1.57, etc. radians. Now let's write an equation to get theta 6 using the value in the lower left-hand corner of the matrix. Theta 6 is the arc cosine of negative R36, the third row, the first column, divided by the sine of theta 5, which we can now use because we've already calculated it. And here we'll print out what theta 6 is. So I'll copy this line, paste it here, and I'll say theta 6 is equal to theta 6, and let's run it. So theta 6 is 0 radians. Now that we have theta 5 and theta 6, we can use one of the other values in the matrix to get theta 4. I'm going to use the third column, the second row. So let's do theta 4 is NP dot arc cos R36, the second row, the third column, divided by the sine of theta 5. And then we'll do another print statement, this time of theta 4, and then run. And it looks like theta 4 is 0 radians also. Now, keep in mind that there is often more than one solution possible here. And since we're only using 3 of the 9 rotation matrix elements to get our answer, we can sometimes find a solution that isn't right. We always need to check our answer before we accept it and send the commands to the robot. We check it by putting the variables back into the rotation matrix to see if it comes out right. Let's do that here. I'm going to create a variable called R36 check. Here, I'm going to type in very carefully exactly the matrix that we derived for R36. So, it will start out with negative NP dot sine of theta 4 times NP dot cosine of theta 5. And I'm going to just continue typing this in, and I'll skip ahead a little bit here. And we've typed in the whole R36 matrix as the variable R36 check. And it looks like this. Now I'm going to print the R36 check matrix and see if it matches the original R36 that we wanted. I'll copy this line, paste it down here, print R36 check, and then run the module. I want to now compare the R36 check against the R36. At first glance, it looks like they're not equal, but if you look carefully, you'll see that they are. For example, this number in the upper left-hand corner, it says negative 0.000000, etc. This number is 0, and it matches the 0 up here. This number here looks like it might be 6, but notice that it's e to the minus 17. This number is also 0, and it matches the 0 here. So this matrix says 0, 0, 1, negative 1, 0, 0, 0, 1, 0, which matches the original R36 that we wanted. It means that our solution that we found is valid. You can use this method to solve for theta 4, theta 5, and theta 6 for any R06 matrix that you could possibly want. So you can plug in all kinds of different R06 matrices here as long as it's a valid rotation matrix according to our two rules. You should be able to get a valid theta 4, theta 5, and theta 6 solution out here.